Good afternoon. I hope lunch was great. We had an awesome morning session, and now we're going to get into the afternoon session. I'm going to start with Eric and Osiris from World, where they're going to talk to us about priority block space for humans and peer-to-peer flashblock propagation. Give it up for them.
Clicker? Wait, what is it? All right, guys. Yeah, thanks so much for coming in to listen to our talk. We're super happy to be here at Frontiers. My name's Eric, or you might see me around on GitHub as Forerunner, and this is my buddy Osiris.
Yep, and we're going to talk about priority block space for humans and P2P Flashblock propagation today. Cool. So we're going to start with priority block space for humans. The goal of this talk is to give you guys an understanding of the mechanics and how it works. So this is a Flashbot, or this is a quote from DMARS from Flashbots. Where bots create congestion, PBH is a highway for humans. And this is how we see it. PBH is a fast lane for World ID users on World Chain. So why PBH? Like, what is the rationale behind PBH? We analyzed over 700,000 blocks on World Chain, and bots used 20% of gas but paid less than 0.4% of fees. And bots and automated systems regularly consume over 50% of the block, and this is a general OP stack trend. We see automated systems spamming priority fees to try to target one specific point in the block, and it crams block space, and everyday users have to pay higher fees and see longer latency as a result. So enter PBH. PBH, at its most fundamental level, introduces a new ordering mechanism into the block builder. So we split block space into two categories with the primitive of World ID, where one subset of the block space at the top of the block is for verified World ID users, and the other subset of the block is for non-verified users. And within each subset of the block, we order with the canonical max fee ordering policy. So the PBH stack is composed of World ID is the basic primitive. Rundler, built by Alchemy, is a custom implementation of a 4337 bundler that we use. The PBH 4337 contracts, obviously World Chain is built on the OP stack, and our block builder is built on top of the REST SDK. And I didn't mention it in this slide, but we also integrate rollup boost, which allows us to have an external block builder within the OP stack. So World ID is a primitive that we built at WorldCoin. It is a set gated by the entry point being the orb. It's a Sybil-resistant set, and our semaphore circuits allow any user that's within the set to anonymously prove their inclusion in the set. And it allows a user to generate a Groth16 proof on device without sharing any secrets that they can use to prove on-chain or off-chain to any verifier that they're a part of the World ID set. There's two important public inputs to the circuits. One is the signal and the external nullifier. These are chosen by the verifier. And it's usually some external context related to the action ID that I'm verifying the proof against. But in the case of PBH, we use the signal as a commitment to the user operation. So it's the user op hash. And the external nullifier is a commitment to the date and a monotonic nonce increment that is equivalent to the amount of PBH user operations sent within a time frame of a month. Cool. So rollup boost, this is a very oversimplified diagram, but this is the basic flow. all consensus messages from OP node flow through rollup boost, and then we split those messages between OP-geth and our block builder. So OP node is going to tell rollup boost to build a block. Rollup boost will multiplex that fork choice update to OP-geth in the block builder. OP node will ask for the block, and then that get payload will be multiplexed again between the builder and OP-geth. Rollup boost then validates the payload of the builder through OP-geth with a new payload call prior to feeding it back to OP node. So this is a redundant system. And if it fails validation or times out or otherwise, we'll always have OP-geth is like the canonical block builder to fall back on. But in the happy path, every payload from the builder is used. Cool. So this is the basic flow diagram of the 4337 contract architecture, at least from from user operation to bundler through the contracts. And so we introduced 3 new contracts to the canonical 4337 stack: the PBH signature aggregator, the PBH entry point, and a custom 4337 module attached to our users' smart accounts. And so the basic flow here is user crafts a user operation. They overload the signature field with an encoded payload that has both the world ID proof and some peripheral metadata like the signal and external nullifier. They send that off to the bundler. The bundler will then validate the user op through the smart account. The 4337 module will determine if it's a PBH user operation or not, and if it is, it will return the authorizer as the PBH signature aggregator. And the bundler uses the signature aggregator as a grouping operator in the mempool. So all PBH user operations will be grouped together. And this is just how bundling works with all aggregators. So it's a really nice primitive to bootstrap off of. So we get PBH user operations grouped together. From this point, the bundler will call handle aggregated ops, and it will overload the aggregated signature field with actually every payload encoded within every user operation's signature. And then the PBH entry point will verify all signatures. After that point, it will proxy the call into the normal entry point contract for 4337. The one other niche thing here is the entry point will call out to the PBH signature aggregator to validate the signatures, at which point it will call back into the PBH entry point and verify that the hashed ops that it sees are the same as the hashed ops that the PBH entry point saw. And what this does is it creates a cryptographic link between the signature aggregator and the PBH entry point, such that the bundler has no control over whether the PBH user operations go to the entry point or the PBH entry point. It has to go to the PBH entry point to not revert. So the bundler cannot turn a PBH user operation into a regular user operation if they wanted to. And so block production within the world chain builder really boils down to 3 main components. The Reth SDK made this super simple to build. It comes down to world chain ordering, which implements the PBH ordering invariants, the world chain transaction validator, verifying the semaphore proofs, and the world chain payload builder actually executing the transactions. And the rest of the node is just bootstrapped off of Reth. And so here's a code block, just a simple code block of how we actually implemented the ordering within the world chain builder. As you can see, super simple. We just added a isPBH field bool to our own priority, which is the world chain priority. And this determines the order of transactions that are coming out of the transaction pool. And then as you can see, we just check if a PBH payload is attached to the pooled transaction type. And if it is, we set it to true. And that's really all we needed to do to override the ordering invariance from Wrath. Here's another code block. This is the PBH transaction validator. And it's very simple. Its only job is to check the target on the transaction. If the target on the transaction is not the PBH entry point, it just goes through the OP transaction validator. Otherwise, we validate PBH. And at this point, we'll attach the PBH payload, the PBH payload to the pooled transaction type after decomposing the call data, and then we'll verify all semaphore proofs attached to the bundle. And if it fails that, then if it fails transaction validation, there'll be a custom RPC. Will be realized by the client with a custom RPC error. And the payload builder, also super simple. Basically, Blockspace is split already into two categories just through the ordering mechanism. Validation is just basically validating that nullifier hashes associated with the proofs. There's no duplicate nullifier hashes within a single bundle, which wouldn't be caught by the contract. And then execution just comes down to executing verified transactions up to the PBH gas limit, which is a proportion of the block gas limit, and then executing non-verified transactions up to the block gas limit.
All right, incredible. So I'm going to change gears a little bit, and we are going to talk about peer-to-peer Flashblocks propagation on World Chain. So just to give you a really quick primer of what Flashblocks are, and I'm sure most of you already know, unless you've been hiding under an OP stack-shaped rock. But Flashblocks are basically taking a big OP stack block, chopping it up into equal chunks by time, and then we propagate those blocks out to the network, and then nodes can consume them, and then use them to serve more up-to-date state to people who are requesting it. Why is this cool? Why do we want Flashblocks? I think there's like one really obvious answer, and that's UX. So basically, when you submit a transaction on World Chain, you can, instead of waiting 2 seconds, wait about 200 milliseconds. So we're thinking about an order of magnitude improvement in UX for your transaction to land on chain, and you can see your little green check mark pop up on your DeFi app. Another one is more frequent MEV auctions. So rather than having one big MEV auction at the end of a big block boundary, we can instead have a lot of small ones. So instead, we'll have 10 for each block. Why is this good? This will make more frequent, but also smaller arbitrage opportunities. And smaller ARB opportunities, we don't know for sure, but we hypothesize we're going to have more efficient markets because of this. And then another one, which I'm going to touch on at the end of this presentation, is higher throughput, but I'll leave that hanging there for now. So I want to talk to you about the peer-to-peer propagation layer, but before I do that, let me talk about how Flashblocks are propagated right now. And the basic idea is rollup boost, which Osiris was explaining how that works before, sends a fork just updated with payload attributes to the block builder. The block builder says, oh, sweet, OK, I'll start making blocks, and also send those flash blocks back to rollup boost. Rollup boost sort of now acts as like a middleman, and then forwards those flash blocks over to a WebSocket proxy, which then fans that out to the rest of the network as a whole. This works, obviously, but we think we can do just a little bit better. So we have this architecture diagram that Osiris showed earlier, but this time there's a little bit more to it. You can see now this is depicting a high availability framework. So rather than having one builder, one sequencer, we've actually got N of them for better uptime guarantees. And you can see there is no communication from World Chain back to rollup boost for Flashblocks specifically, and those are now propagated over the existing RLPX peering framework directly from the builders over to anyone who wants them. So let's talk about some of the things we want to maintain with peer-to-peer propagation of Flashblocks. So we want per payload, per builder authorization. So we want to be able to change which builder is building per block So how we do this is essentially rollup boost, when it sends a fork choice updated with payload attributes, also attaches an authorization. And all that authorization is essentially the rollup boost signature over the builder's public key and payload ID, so that it can basically have authorization, and other members of the peering network can trust that, yeah, this builder actually does have authorization for this payload to publish these flash blocks. All P2P messages, as it currently stands right now, are authorized. And this is really useful because it means that like random people can't come join the peer-to-peer network and start spamming transactions. We'll know because they're unauthorized, and you can ban them as a peer. And we also want to maintain the same trust assumptions that Rollup Boost currently has. So right now we want to maintain that Rollup Boost is in fact the decider of who gets to publish flash blocks and when they get to do it. So the obvious question and sort of a hard problem to deal with is we've got a busy kitchen, we've got an HA framework, and we have multiple builders who could all attempting to be published at the same time. So some of you may know that with OP-Stack HA, there's an entity called OP Conductor, and that manages which sequencer is actually active, and thereby which builder is also active. But during a failover situation, you can have basically where we're switching from sequencer 0 to 1, and therefore builder from 0 to 1. But there is a one block area where we could have two builders potentially thinking they're building at the exact same time. This is obviously really bad because the whole core premise of flash blocks is when we publish them, we're guaranteeing, hey, this is a real flash block, it will land on chain, and we really don't want to break that promise to users. So if we've got two builders also publishing at the same time, that obviously violates that. The solution is really simple, and we can just publish start and stop signals along this P2P network. So basically how it works is a sequencer failover happens, a new builder starts building, but they're going to go, hey, I want to start building. They publish that to the network. The current builder will receive that and go, oh, OK, I'll stop. And they publish that stop signal to the network. And then when the new builder receives that, they can go ahead. And I know a few of you are already thinking, that sounds way too simple. That can't possibly work. But it can, because we actually have Raft consensus operating in the background on OP Conductor. So if there is some sort of race condition in this peering layer, we can actually just wait one block for Raft to figure everything out and then proceed from there. So we can keep it nice and simple. And the peer-to-peer network is obviously aware of, there might be bad actors on this network. There might be people who are potentially trying to censor flash blocks or do something else nefarious. So we have a reputation system where we basically dish out reputation penalties for people that submit bad messages, messages that we've already seen. Maybe they're trying to replay messages back to us. We can just dock the reputation, and eventually we'll ban them. And now I'm going to touch on the thing I mentioned earlier, which is how do we increase throughput on World Chain, or for anyone else who is consuming flash blocks. And this is with incremental execution. So this has been touched a few times already in the talks today. But this actually basically bumps that up and takes it to the next level. Because now instead of incrementally computing the state root as we're executing transactions, we're actually getting the block before it's published, or parts of the block. We're getting the flash blocks before the real block is actually there. So as we receive flash blocks, we can execute those transactions. We can incrementally update our state root. And optimistically, we're doing this. And then at the end, when we receive the total block, all we have to do is verify, oh, yeah, these flash blocks were real, validate that the transactions actually did land on chain in the order we assumed, and we're good to go. We're already done. State root computation over. Yeah, that's kind of all I wanted to share with you guys on peer-to-peer flash blocks. We've been working pretty hard on this over the last month. This is the team over at Tools for Humanity, which is the development entity for WorldCoin. And yeah, we got a lot of cool Rust engineers. We're doing cool stuff all the time. Yeah, we're always hiring. So if there are any Rust engineers in the crowd that are looking for to work on cool projects like us, then yeah, feel free to reach out. We've got tons of partners that are here, especially big shout out to Flashbots, who this wouldn't be possible without, and with Paradigm. Everything that we're doing here is built on Reth. So I mean, obviously, none of this would be possible without all of the awesome devs in this room. And yeah, I think that's time for questions. So if anyone's got any burning questions, hopefully we've got some good answers for you. Thank you. Cool. All right. Sounds good. All right. Thank you, guys. Appreciate it.